extreme gradient boosting, and because it is separated to three parts, we will first try to understand what is boosting, then what is gradient boosting, and then we'll take it to the extreme and understand what is the extreme gradient boosting. And we will depict each part will serve a different paper. The last part, the extreme gradient boosting, will serve the paper by Yankee Chen, the inventor of XGBoost. The gradient boosting part will serve the paper by Friedman from 2000. And the boosting part will serve this paper by Yoav Grund and Robert Shapira, who invented AdaBoost, which was a breakthrough in machine learning back in the 90s. So we'll start with boosting. Ensemble modeling is the process of running two or more related but different analytical models and then synthesizing the results into a single score or spread in order to improve the accuracy of predictive analytics and data mining applications. In this session, we will consider two of the main approaches in ensemble modeling, bagging and boosting. So bagging, short for bootstrap aggregation, is an ensemble modeling technique in which we combine many weak independent learners by means of majority votes for classification problems or mean in regression problems. A familiar example is random forest. On the other hand, the boosting method employs the logic in which the subsequent predictors learn from the mistakes of the previous ones. Therefore, the observations have an unequal probability of appearing in subsequent models, and ones with the highest error appear most. The predictors can be chosen from a range of models, like decision trees, regressors, classifiers, etc. Because new predictors are learning from mistakes committed by previous ones, it takes less time or iterations to reach close to actual predictions. But we have to choose the stopping criteria carefully, or it might lead to overfitting on training data. So gradient boosting will be an example to boosting, and which will be followed by XGBoost. So the intuition for boosting is as follows. Assume you are given a previous model M to improve on. That is, you build a model and you ran it on your instance at X, and you receive the predictions Y with some error epsilon. So Y is the output, X is the input, and X is our model applied to the input, and epsilon is the error. Now, what if we are able to see that the error is not white noise, meaning that we can develop a model on this error term, like epsilon is some other model, G, of the input, X, and with a new error, epsilon 1. So probably you'll see that the error rate will improve to a higher number, let's say 84%. That is, if we combine the new model for epsilon inside the prediction in the original model, right? So if we take epsilon and place it over here, then we'll have y equals mx plus gx plus epsilon 1. And this prediction will be better than the original prediction because we've modeled the error itself. Now, what if we can repeat this process and also model epsilon 1 with another model, let's say h of x? Then we'll have another error, epsilon 2. So you can see that we can do it recursively, and the accuracy of the obtained model, right, if we unfold it back to y, will probably be better than that of the original model. Why? Because each time we used our original data to model the error. So we'll get an error epsilon 2, and now maybe we can even improve it even further? Well, the answer is yes, because we can sort of attach to each model some kind of parameter that indicates the accuracy of the specific model that we've built. Meaning, if M was found to be very accurate, then we'll attach to it the parameter alpha that is relatively high, and so on. So we'll get a linear combination of each of these, we call it weak learners, and we'll get an error epsilon 3. Now, what I'm trying to say is that probably for the training set, epsilon 3 will be a lot smaller than the original epsilon. So this is the main idea of boosting. And you might have two questions as you review this approach. The first is there even non-white noise? Meaning, can we even model the epsilon with a model of its own? So this is actually the first Kahoot question. You have here 4 options. You will be able to select either one of the shapes, either a triangle, a circle, and so on. And the question is, why is it possible to build a model for the error term? And the answers are because the learners are weak, because there are multiple learners. It's always possible to model the error terms, and actually, usually it won't be possible. So you have 20 seconds to select the correct answer, starting from now. Okay, so thank you for selecting the answer. The next question is, why not achieve 100% accuracy? Meaning, why not repeat this process recursively again and again? If we know that in each iteration we are improving the accuracy, then why not do it endlessly? And the answers are, at some point the error can't be modeled. To avoid overfitting, repeating it won't reach 100% accuracy, and it will take a lot of time and resources. So you have 20 seconds from now. Wow, amazing results. Okay. Okay, so the answers are, the reason there is no white noise is that each weak learner we saw is actually weak, meaning that had these weak learners been strong, meaning they could find the real connection between the input and the, let's look at the first weak learner. Had it been strong, then it would have found the real connection between the input X and the output, and then the error would have been a white noise. But because those are weak learners, then there's a lot of non-white noise, a lot of correlation still left to be found. And the reason we don't do it endlessly is to avoid overfitting, as most of you said. Okay, so now we know that boosting combines weak learners, also known as base learners, to form a strong rule. An immediate question which may pop in your mind is how boosting identifies a weak rule. To find a weak rule, we apply base learning, machine learning algorithms with a different distribution. Each time a base learning algorithm is applied, it generates a new weak prediction rule. This is an iterative process. After many iterations, the boosting algorithm combines these weak rules into a single strong prediction rule. Here is another question which might bother you. How do we choose a different distribution for each round? And here is the template for choosing it. So step 1, the base learner takes all the distributions and assigns equal weight or attention to each observation. And step 2, if there is any prediction error caused by the first base learning algorithm, then we pay higher attention to observations having prediction error. Then we apply the next base learning algorithm. In the third step, we iterate step 2 until the limit of the base learning algorithm is reached or higher accuracy is achieved. Finally, we combine the outputs from the weak learners and create a strong learner, which eventually improves the prediction power of the model. boosting pays a higher focus on examples which are misclassified or have higher errors by preceding weak rules. So let's look at an example which clarifies this template with an algorithm called XGBoost, which was the first real boosting algorithm. So without diving into the math behind this algorithm, we'll have enough math later on. Let's just consider a simple example that demonstrates it. Suppose we're given the upper left box of positive and negative examples which we'd like to classify. Our weak learners will be decision stumps whose boundary is a straight line in the space. Then our first learner will take care of classifying correctly the leftmost positive examples, those found here. Okay, so the first learner chose to split the data over here. So thus the first weak learner is wrong about all the positive examples to the right of the decision boundary. Why? Because the first learner says, okay, all those to the left over here are positive, all those to the right are negative, and so he was wrong about these three positives. Therefore, we will consider those positive examples as having a higher weight upon building the second base learner. This is why they appear to be slightly larger in box 2. Since they have larger weights, the decision boundary will this time pay more attention to them and will classify them correctly. So this is why the decision stump was selected over here. So we continue to build the weak learners this way and end up with box 4, which is the boosted learner, the combination of all those three boxes. So you can see that in the boosted box, we have all the examples classified correctly. So let's cover something you all must be familiar with, but just to align, the bias-variance trade-off intuition. So a common challenge with machine learning algorithms is the trade-off between bias and variance. To illustrate it, let's consider the following problem in this picture. You are asked to fit visually a step function given the input data points on the upper left corner of the image. Which solution among the three do you think is the best fit? Meaning, will this line be the best, maybe this one, or this? Well, the correct answer is marked in red. And why? The general principle is we want both a simple and predictive model. While the upper right model is too complicated, which will make it hard to generalize, and the lower left model isn't predictive enough, which means that it doesn't even give good results for the training set, the lower right model is both simple and predictive. This trade-off between the two is also referred to as the bias-variance trade-off in machine learning. Typically, increasing the complexity of machine learning models results in two phenomena. One, the prediction power increases for the training set, and you can see it over here in this line. The prediction error drops consistently for the training set. And it ends up decreasing for the test set, meaning the test error decreases, but eventually increases. And this point, this sweet point over here, is where we just minimize the test error and avoid overfitting. So we might want to stop the model training at this point. However, often XGBoost drives the training error to 0, and at the same time, further iteration often continues to improve the test error. So you can see here, for example, that at the point, by the time the training error, which is in green, reaches 0, the test set continues to drop. So we don't have overfitting. And this phenomena actually shocked the scientific community when it was first introduced. And this is one of the reasons that the XGBoost creators won the Gödel Prize in 2003. And by the way, one reason for that phenomena is that as iterations proceed, the impact of change is localized. So let's compare bagging and boosting. So first of all, both methods allow any number of weak learners. Both methods apply random sampling with replacement across different iterations. However, in boosting, the sampling is conducted over weighted data. In bagging, the model is built parallelly. In boosting, it is built sequentially. In case of regression problems, in bagging, the aggregation is a simple average, while usually in boosting, particularly in XGBoost, the aggregation is a weighted average based on the accuracy of each separate weak learner. While in bagging we keep any weak learner that's been learned, in boosting we may opt to discard it in case it isn't good enough. And this graph is just a cartoon. However, it is often the case that boosting outperforms bagging in terms of error rate on the test. So just to be more concrete, XGBoost will beat random forest. And let's move to the next question. Which framework, boosting or bagging, tries to reduce bias and variance simultaneously? So you have 20 seconds starting from now. Okay, great. Thank you. So the correct answer is boosting, and let me try to explain this in simple words. So random forest, it tries to reduce variance by building a tree, independent trees that are trying to model the entire data. However, boosting also builds separate trees. However, each tree learns from the previous tree, so we are also improving the training error. Meaning we are fighting not only the variance, the way random forest is, but also the bias. Hope it's clear. So this slide summarizes all the traits of bagging and boosting we've just covered. Feel free to review it upon watching the session recording. It is worth mentioning that, again, while both methods reduce variance and hence provide higher stability, only boosting tries to reduce bias. Okay. So this was the first part, sorry, the second part about boosting. Do you have any questions?
Are you guys still there?
Yep, it was just pretty clear.
Okay, great. So let's continue with gradient boosting. So congrats, you've made it to part 3. As its name implies, the extreme gradient boosting algorithm incorporates concepts from boosting and specifically from gradient boosting. While in the previous part we served boosting, now let's dedicate it to gradient boosting. The 4 boosting methods covered in this part are gradient boosting machines, also known as GBMs, residual refitting, which is a special case of gradient boosting. It's actually something that I sort of invented for this lecture. It's not a real name for an algorithm, but it will make understanding what gradient boosting is a lot simpler. Then there is Iterative, which is also a special case of gradient boosting, and XGBoost is a totally different branch. It's not related to gradient. So residual refitting. Let us begin by introducing this residual refitting method. It's very similar to what we saw earlier in the boosting slide. Let's say we model our output with some model M, and we have an epsilon, an error epsilon. Then we can move sides and say that epsilon is y minus m of x, and then we can approximate meaning build a model on the error, like this, and then we can replace epsilon with epsilon hat, which is the model for epsilon, and get that the prediction for y is actually the prediction from our original weak learner, plus the difference between the actual value and the model value. Okay, so let's try to do it to see an example. Okay. So we'll start with a simple example. We want to predict a person's age based on whether they play video games, enjoy gardening, and their preferences on wearing hats. Our objective is to minimize the squared error. We have these 9 training samples to build our model on. Intuitively, we might expect 3 things. First of all, the people who like gardening also are probably older. The people who like video games are probably younger. And like hats is probably just a random noise. So in our first attempt to build a tree, a decision tree, to this problem, let's say we require the terminal nodes and have at least 3 samples. With this in mind, the regression tree will make its first and last split on like gardening, meaning we only use one feature to build this tree. It's a very, very simplistic tree. Now, this is nice, but it's missing the valuable information from the feature like video games, right? We only use like gardening. So let's try to improve this tree. Here in this improved tree, we pick up some information from the played video game, but we also pick up information from like hats. You can see over here. Okay, but we already said that like hat is actually a random noise. It's not really a good feature. So this means that this tree is actually overfitted. And the reason is that, it becomes apparent because we're using garbage feature. And the reason the tree elected to use this feature is because specifically for the subset of examples that appear in this branch of the tree, that is 13, 14, 15, and 35, specifically for them, it did matter whether they like hats or not. But in the context of the entire data set, like hats is not important. So here we can see that actually decision trees are not robust to overfitting, and this is actually the reason. So let's try another approach. Instead of building a tree, instead of building a complex tree as we just did here, let's say we build the original very simplistic tree, this one, and
I think I missed what we were trying to predict.
The age. So let's say we take the prediction from the first very simplistic tree. We already know that it's not a good tree, but let's just for the sake of discussion, let's just take its prediction. And now let's try to understand how far are we from the real age, from the actual value. Okay, so we call it the residual. So for example, for the first person, the residual is minus 6.25 because this is just this minus 6, and so on. So we get a vector of residuals. So what if we could model those residuals with another tree? Okay, so this is what we'll try to do. Build a tree that will try to predict those residuals given the original feature, that is like the video games, like gardening, and like that. So when we try to build a tree for this variable, the tree 1 residual, we actually get a new tree, which is as simplistic as the first tree, meaning it has only one split. time it involves the play video games feature. So you remember that the first tree in our ensemble included only the other feature, which was like gardening. And now this tree, which is actually the tree for the residuals, uses the other informative feature. So if you are following, you understand that the first tree that tried to model the output directly used only one informative feature. And then when we took the prediction of the residuals from this model and tried to model the residuals and build a tree for the residual, then the tree uses actually the other informative feature. And why is that good? Because if we compare it to what we did the first time, when we built like this complex tree, this one, complex tree involving all kinds of features, including like that. So we said that this was an overfit tree, and now we're just settled with two very simplistic trees that are not overfit. So here we can see actually how we combine those trees all together. So once again, we had our original age. We built a very simplistic tree, a weak learning for the age. We took the residual between the prediction and the age. We built a predictor for the residuals. We take the prediction for the residuals, and then we combine the prediction that is the tree 1 prediction, 19.125, plus minus 3.567, and we get the combined prediction, which is our estimate of the age. And we can see that the final residuals are smaller than the first residual, meaning that we improved our model using a model on the residual. Okay. So just to standardize our iterations, let's make a slight tweak to our model. We tweak it to conform to most gradient boosting implementations. We'll initialize the model with a single prediction value. Since our task for now is to minimize squared error, we'll initialize f, the initial prediction, with the mean of the training target value. By the way, had we wanted to minimize the mean absolute error loss function, then we would have opted to use the median of the observed label because of this formula, the argmin of, well, you can see the formula. So what I just said is that initially we say that the first prediction is actually not of the model. It's like a very simple prediction, like just take the mean of all the labels. And then if we do this, then we are able to get this recursive formula to obtain the n+1 prediction, given that we've already had our first m prediction, and we add to them the model over the residual in each iteration. So that is all nice. But it's very, the method we just saw is very limited to residuals. Like when we want to optimize the squared error loss. We will now show a method called gradient boosting machines that is capable of working in any loss function. And in that sense, it sort of revolutionized the boosting frameworks. So we can see here examples for loss functions that this framework will be able to work with. And just to put things in context, if until now we were only able to boost regression problem because the output was continuous, then now since we will be able to work with for example, a log loss function, then we will be able to work on classification problems. So please note that as we derive the loss function, which is again the sum of squared errors, according to the previous iteration, the previous iteration's prediction, then what we get is the residual. So the derivative of the loss function is actually the residual. And then came Friedman in 2000 and said, well, why not generalize this notion to any kind of loss function? If we just use the squared loss function and we got the residuals, then we can take any loss function and just use its gradient, and this will be the replacement for the residuals we just saw in the residuals refitting example. Okay, so now a very important note which drove me crazy when I first read this article. So contrary to many machine learning algorithms such as the neural networks and linear regression and so on, in gradient boosting, the loss function is being derived not according to the parameters, but according to previous predictions. So we're not optimizing the parameters, but rather the results of the previous prediction. Okay, so it's a very important thing to understand as you read the article later on. Just to make sure we are all following, you have this question in gradient boosting machine, the loss function is derived by, and you can choose 20 seconds. Great. Okay, so what do we do with this formula of this gradient and all this? So recall that the derivative of the sum of the absolute error loss function is actually the sign of the difference between the actual value and the predicted value. Okay, the derivative of absolute value is simply the sign function. So how do we use this notion to kind of work our way through while using absolute error loss function? So let's say we take the same example, and instead of using sum of squared error loss function, we are now saying that we want to optimize that we want to use the sum of absolute value error loss function. So why do we even want to use another type of residual? Why do we even want to? Why not use the method we just saw with the residuals refitting? Okay, so stay with me. It's not so intuitive, but we'll try to explain. So let's get an intuition. So consider the first and fourth training samples. Their F0 value, meaning the original prediction, as we said, is actually the median value of the original of the true label. In this case, it's just 35. So we're just saying that F0, the first prediction, is 35. Now, their F0 residuals are 13 minus 35, which is minus 22, and 25 minus 35, which is minus 10, respectively. Now, suppose we're able to make each prediction 1 unit closer to its target. Respective squared error reduction would be 43 and 19. Why? Because if we improve, instead of 22, we say that the residual improved by 1, then the difference will be 43, because it's squared. function is squared error. And the same over here, if we improve the residual by 1, then actually the loss function improves by 19. So a regression tree, which by default minimizes squared error, will focus heavily on reducing the residual of the first training sample. Meaning, it will know that it can benefit more. It can benefit 43 from optimizing this sample, so it will focus on it. But if we want to minimize the absolute error rather than the rather than the squared error, then moving each prediction 1 unit closer to the target produces an equal reduction in the cost function. With this in mind, suppose that instead of training H0 on the residuals of F0, we instead train H0 on the gradient of the loss function L with respect to the prediction values produced by F0. So essentially, we'll train H0 on the cost reduction for each sample if the predicted value were to become 1 unit closer to the observed value. In the case of absolute error, HM will simply consider the sign of every FM residual, as opposed to squared error, which would consider the magnitude of every residual. So instead of -22 and -10, we'll just have -1 and -1. This will be our sort of quote-unquote residual. And we'll get back to these examples shortly and illustrate it. Let's formulate the gradient boosting algorithm rigorously and then go back to the example we just saw. So let HM be the pseudo-residual prediction tree we built in the nth iteration. And let FM be the aggregated prediction from the previous iteration, meaning HM is simply for example, the tree that we are building for the residual, just as we did earlier. So after samples in HM, in this new tree we built for the residual, are grouped into leaves, an average gradient can be calculated and then scaled by some factor gamma. So that Fm plus gamma Hm minimizes the loss function for the samples in each leaf. Note that in practice, a different factor is chosen for each leaf. Recall that we show in advanced calculus that the function gradient is in fact the direction in which the function slope is steepest. And hence, this is the part of the algorithm where the gradient descent algorithm is applied. Hm is the direction of the gradient in the function space, and gamma is the magnitude or step size that we would advance in order to best approach the local minimum of the loss function. So again, Hm is actually the prediction obtained for the residuals, and it will act as the gradient in our gradient descent problem formulation. And gamma will be some kind of parameter that we will try to optimize such that our step will minimize the loss function. And we will illustrate it with an example. So now we can use gradient descent for our gradient boosting model. The objective function we want to minimize is L. Our starting point is F0, and for each iteration, for iteration m equals 1, we compute the gradient of L with respect to F0. Then we fit a weak learner to the gradient component. In the case of a regression tree, leaf nodes produce an average gradient among samples with similar features. For each leaf, we step in the direction of the average gradient using line search to determine the step magnitude. So line search, when I say line search, I mean we're trying to find the gamma that optimizes, that minimizes this whole term, given the prediction HM on the residual from the previous iteration. So, and the result is F1. Then we can repeat this process until we have Fm. We'll now clarify the algorithm with an example. So let's get back to our aforementioned example. So we start with a constant prediction f0. As we said, it is just the median of the true labels. In this case, we just see that the median is 35. The next step is to calculate the pseudo-residual. Just calculate, meaning if we take 13 minus 35, and we take the sign of it, then it's minus 1. But for example, 68 minus 35 is, the sign is positive, so it will be 1. Then we will try to model this kind of vector with our original features. And once we do model this vector, we get predictions from the model for those pseudo residuals. And this is the result of the prediction. Now, what we want to do is we try to find for each leaf in this model, in the model that we built for the residuals, we try to find its own gamma, such that taking the previous prediction, that is f0, and adding to it gamma times h0 will minimize the loss function. So, and this process is actually it's called line search. We're just searching for a single parameter value that will minimize a known function, and we will obtain those values. And then we repeat this process. Now that we have both h0 and gamma 0, we can calculate f1 to be f0 plus h0 times gamma 0, which in this case is just 14.5. And this is actually the second the prediction from the second iteration. And now we repeat this process. We calculate the pseudo residual for f1 with respect again to age, to the original, to the raw feature. And we say that, for example, that this is 13 minus 14.5 is again minus 1. I mean, the sign is minus 1 and so on. And again, we build a tree for these pseudo residuals. Those are the predictions of the tree. We're trying to find the gamma that minimizes the loss function for the expression f1 plus h1 times gamma. And this is the calculated gamma. And from this, we calculate f2 in the same manner. So f2 is supposed to be much better, for sure, from f0, but also from f1. You can see that the ages here are much more closer to the actual ages. So, let us introduce some regularization techniques that are used in gradient boosting machines. Recall that regularization means reducing the model's variance or tendency to overfitting by reducing its complexity artificially. Here, we introduce a term you might already be familiar with called shrinkage or learning rate. The concept is fairly simple. For each gradient step, the step magnitude is multiplied by a factor between 0 and 1 called the learning rate. In this formula, it's mi or v. In other words, each gradient step is shrunken by some factor. Shrinkage appears to be empirically effective because it causes sample predictions to slowly converge towards observed values. As this slow convergence occurs, samples that get closer to their target end up being grouped together into larger and larger leaves, resulting in natural regularization effects. So here we have a new Kahoot question. So the question is, in the image to the left, which curve probably follows from the lowest learning rate? You can see here that we have the error rate on the y-axis and the iterations on the x-axis. So for example, you can see that the red curve starts with very high error and slowly drops to a very low error. contrary to all the rest of the curve. So the question is, which curve probably follows from the lowest learning rate? Go ahead, you have 20 seconds starting from now. Okay, so the correct answer is that the red curve has the lowest training rate, and we can see it because it really slowly reduces the error and converges to the lowest error. So, for example, the purple curve is trying to do something very aggressive. In each iteration, it will advance in the gradient direction very aggressively, and so the error will drop significantly, but then we might skip or miss the minima, and then the error will continue to rise.
And what about the green line?
So probably somewhere in the middle.
So Amir, quick question on this one actually. So the starting point of each curve, is it showing the first iteration or this, the zero approximation that every curve is supposed to start with?
So the starting point is, I mean, you've asked a valid question, but actually we should relate only to the derivative of the curve, right?
Okay, that makes sense.
So yeah, it's a good point, but only the derivative should be taken into account for this question, right?
We also can look at the curvature of the line.
Yeah.
It's also the indicator.
Yeah, right. Okay, so another regularization technique is row and column sampling. Most gradient boosting algorithms provide the ability to sample the data rows and columns before each boosting iteration. This technique is usually effective because it results in more different tree splits, which means more overall information for the model. The final regularization technique we'll consider for GBMs is adding constraints. We could apply constraints on the following parameters of the tree: the number of trees, tree depth, the number of nodes or number of leaves, the number of observations per split, and new improvement to loss. We won't get into too much details for this slide. Actually, I have here an example. I really wanted to show you an example for gradient boosting from start to end. I'll try to do it really quick so that we'll have enough time for XGBoost. So let's take a look at this example. We have only 3 explanatory variables and 1 target variable, salary. Okay, we want to model the salary given those variables. Now, for the simplicity's sake, let's assume that we're only building 1 tree, n equals 1. We start with an initial constant model, f0. Now assume that the sum of squared error loss function is being used. This is the loss function that we want to use for this problem. So the initialization for the prediction will, as we said, is the average of the original label. So in this case, 5,008. So we say that f0 is the same for all the instances. Next, we calculate the gradients with respect to the initial prediction. In this case, the gradient is just the residuals. We saw that actually the gradient in the case of the squared error loss function is just the residual, meaning the difference between the actual label and the predicted label. So it will turn out to be just yi minus the previous prediction, which is 5,008. So we can calculate the residuals as follows. So for example, if 10,000 minus 5,008, which is 4,991, and so on. So now that we have the residuals, we will try to build a model on the residuals. And this is the decision tree that we build for those that is being learned automatically for the residuals. Now that we have this residuals tree, what we want to do is to find a constant lambda such that the loss function between the actual value and the new prediction, which is the previous prediction plus some lambda times the prediction from the tree we've just built, is minimized. So again, we want to find a lambda that will minimize the how far are we from the original label. So what we can do is just calculate h of xi for each I. Again, h of xi is the prediction of the residual tree for each of the instances. So, for example, for the first instance, we know that f0 is 10,000. y1 is 10,000, and then f0 is 5,008.3 plus lambda times the prediction for the first instance. Prediction from the first instance just turned out to be 4,091 in the residual tree. So we're just placing it over here. And so we calculate a term for C of lambda, which we want to minimize. So, and we minimize it, this is already not so interesting, we can minimize it with gradient descent or whatever, and we find a lambda that minimizes this term. And now that we found it, we can say that our final prediction, F1, will be F0 plus, let's say we found the lambda to be 0.5, so it will be F0 plus 0.5 times the residual tree h of x. So, for example, let's say we had some observation. So, to give the final prediction, we'll take the original prediction, which actually was the average. We add to it the lambda that we found, times the result of the residual tree or the gradient tree applied to this prediction to get the final prediction. So this is the main idea of gradient boosting machines. If you have any questions, feel free to ask right now. Okay, great. So let's continue to extreme gradient boosting, which is actually the most interesting part of this lecture. Assume you are given a data set with n examples and n features, denoted as the pairs xi and yi. So, given some 5 examples and a tree, we classify them according to simple rules on the vertices of the tree, and their score is then the weight at the tree's leaves to which they had been classified. So, for example, the number of leaves T is 3, okay, and the weight of the tree is +2, 0.1, and -1. So how does let's say we already built the tree and everything is okay, so how does the model end up giving us the result for a new instance? So let's say we want to calculate the final score for the boy. Then we find all the trees in which the boy appears. We see that it ended up being diverted to this leaf and also to this leaf. So the final score for the kid will be just plus 2 plus 0.9. Okay, so we do it for all the inputs. So now let's take a look at the model. Generally, a tree ensemble model uses k additive functions to predict the output, where curly f, you can see here, is actually the space of regression trees, and q over here represents the structure of each tree that maps an example to the corresponding leaf index. T is the number of leaves in the tree. Each fk corresponds to an independent tree structure q and leaf weight w. Unlike decision trees, each regression tree contains a continuous score on each of the leaves, and we use wj to represent the score on the jth leaf. For a given example, we will use the decisions rule in the tree given by q to classify it into the leaves and calculate the final prediction by summing up the score in the corresponding leaves given by w. So let's just reiterate because it's important to understand those terms. So our final score will be just a linear combination of the scores from each tree separately. Each tree is denoted by fk, and each tree can be described by two parameters, w and q. Q is actually the structure of the tree, meaning the splits and how we decided to do the splits and the features and so on. And W is the scores at the leaf of the tree. Make sense? Makes sense. So another question, what does W stand for in the previous formula? And you have 20 seconds.
Some guys cannot enter the application.
The code is sometimes has this issue. You can't go in.
Yes. They try it through the web. But
okay. I hope it's only for this question. Okay. Great. So yeah, the answer is the W stands for the weight in the. So now that we know how the model will end up being built, let's take a look at the learning objective, what we want to optimize. So let's say our loss function is lowercase l. So given our training set, we want to minimize the sum of the loss function over all the instances, where each loss function is between the predicted value yi hat and the real value yi, and we want to edit a regularization term which will punish really complex trees. So omega here, in the case of XGBoost, was selected to be a gamma times t, where t is again the number of leaves of each tree, gamma is some hyperparameter, and plus half times lambda w squared, where lambda is again a hyperparameter, and w squared is just the sum squared of the weight on the scores on the tree leaf. So you can see that if we give higher value to gamma, then we will punish more on models that have a large amount of leaves, and so on. So this is the bias reduction term, and this is the variance reduction term. The first term is just meant to make better predictions, and the first term is meant to avoid overfitting. And the reason that XGBoost elected this kind of variance reduction or penalty is that it's just amazing how it arranges mathematically, and later on we will see. Okay, so prediction notation. Let's say that the prediction of the ith instance we denote it by y hat I, and if we focus on the tth iteration, then we add this subscript t. So what we want to optimize is the objective function curly L, which is the sum of the loss function lowercase l between, again, the actual value yi, and for each iteration, the previous iteration prediction plus the prediction of the current iteration tree, which is ft. And to that, we want to add the penalty for the given tree ft, for the new tree that we want to add to the ensemble. So the algorithm is to greedily add the seek for the ft that most improves our model, right? It's impossible to do it not greedily. It's like a very hard problem. So once again, this whole term altogether is the new prediction for the tth iteration for the ith instance.
Okay, but the addition to the whole loss function, not to the specific omega, to the whole.
You're speaking about the omega. What is omega? So omega is the complexity, is a term that stands for the complexity of the new tree. Only the new tree, not the whole tree. Only the new tree. So let's make a slight digression, which will be essential to understand what's going on later on, and talk about a little bit about the difference between gradient descent and Newton's method, which are both optimization methods. So let's say we want to find the minimum of this green function over here. We start with an initial guess x0, and we want to do some iterative steps to reach the minimum. So in gradient descent, what we do is we calculate the tangent slope. We see that the direction leads us to the left, and then we will make some steps leftwards, to the left. In Newton's method, we do something more cool, right? We try to approximate our original function, our green function. We try to approximate it with a red curve, like order 2 polynomial curve, and then we find the minimum of this curve. Now that we found the minimum of this curve, we'll say, okay, so this minimum will be our next guess for the minimum of the green curve, and so on. For x0, for x1, we will once again try to approximate the green function with the red function, minimize it, and recursively converge towards the minimum of the green curve. This is Newton's method. One other mathematical term that will be important to understand XGBoost is Taylor's expansion. So in Taylor's expansion, what we do is we take a look at, for example, this sine function, the blue one, and we approximate it near 0 by using this odd order polynomial, such that we are able to calculate the sign near 0 with some really good accuracy. We can see that both curves are nearly the same, around 0. And more generally speaking, this is the formula for a Taylor series for any function f. Maybe just let's take a look at the first term here. If we want to calculate the value of f at a point x which is close to a, then what we can do is we take the value of f at a, add to it the derivative of f at a times the difference between the two, divided by 1 factorial, and so on, recursively add second, third order derivatives, and so on. So this is the Taylor series approximation. Why do we need it? So if you take a look at this term that we want to optimize, what we're actually looking for at the Tth iteration is we want to find the tree Ft, which will minimize this loss function. But it's absolutely impossible to do it by just guessing and trying to plug in different trees each time. So what we will want to do is try to approximate this term to make it easier to optimize. And the way to do it is with Taylor series. So we'll call this term, that is the prediction from the previous iteration, we'll call it A. And then X will be this entire term. So if we talk in terms of the previous formula, and we plug the X and A from the Taylor series formulation, then we get this formula, where GI is just the derivative of F from the Taylor series at the point A. This is just a notation. And Ft of Xi is X minus A, right? It's just, if this entire thing is X and this is A, so X minus A is just Ft of Xi. And similarly, we call Hi the second derivative of F, and Ft squared is X minus A squared. So now, why did we do it? Why did we even want to do it, right? Because look at what happened here. Previously, we had the loss function between the original value, yi, and some really complex value. What we have now is the loss function between yi and the previous prediction, and we add to that externally, that is not inside the parentheses, but externally we add to that some kind of linear combination of the derivative of the loss function. Why is that good for us? Why do we even care about it? Because now that we want to optimize on that, then this term is actually constant. Why is that constant? Because we actually calculated previously, in the previous iteration, the prediction for y hat at t minus 1. So this is already calculated, given that we want to optimize for the new iteration. So our only variables in this kind of approximation of the loss function are left over here. And since this is constant, then as we try to optimize curly L, which is the objective function, we can discard this orange part. So once again, let's reiterate, because this is the most beautiful part in the XGBoost. We had this complex, really complex term for lowercase l, which is our loss function. We said that we cannot try to plug in different values of Ft to get what would be the best next tree in the ensemble. So instead, we are approximating L, dividing it to different parts with a linear combination of the derivatives. And now that we've done that, the loss function is constant, and once we derive it, it can be ignored. By the way, the GI and HRI stand for gradient and Hessian, respectively. The first order derivative of the loss function with respect to the previous iteration's prediction, and the second order derivative.
Hessian matrix.
Yeah, exactly. In this case, it's scalar, yeah. But in overall case. Okay, so if you understood this, then this is the most important thing about XGBoost. Everything from now on is just algebra. Okay, so we'll do some really cool algebraic tricks, but it's just tricks. So let's denote the set of examples that were classified into the J cliff by IJ, meaning ij is all the instances that found themselves in the J's list. For example, here the boy is in I1 and all those three guys are in I3. So we can do a simple trick. I won't go too much into this. It's also not that important. But we can rewrite the term sum of the IFT as follows. What we do is we separate to the different leaf sets and so on. After we do it, we can simplify the term that we saw earlier, and we can rewrite it in terms of the sum over the leaf set. Once we do that, we are able to also plug in the regularization term. The lambda sigma wj comes into the parentheses, and this is very cool algebraically because this explains why we even wanted to use this kind of term. So now that we have this the objective function formulated as follows, what we want to do is we want to assume that we already know the structure of the tree, and we want to find the optimal weight of the tree. So if we want to find the optimal weight of the tree, the best thing to do would be to derive the objective function according to the weight. So we'll derive the objective function by each wj separately. I will spare you the calculation, but what we receive here is that the optimal weight for the jth node is just the sum of the gradients for all the instances in this node divided by the sum of Hessians plus lambda. Okay, so please note, this is what we did here is actually Newton's method. Okay, because what we did is we approximated function with a Taylor series and with a quadratic function, and then went and minimized this quadratic function. And then the minimum of the quadratic function, we said this would be our kind of guess for the optimal value. So some things to note about this formula. You can see that we have in the denominator the gradient, and sorry, in the denominator we have the gradient, and in the denominator the Hessians and the lambda variable. So two things I have to note here. First of all, let's consider the end case where the gradients are all zero. Okay, let's assume that all the GIs are zero. Then what we will have here is that the entire term will be zero and Wj will be zero. Now, what does it even mean? Why is this the case? So it turns out that if all the gradients are zero, it means if you think about gradients as residuals, like in our discussion on gradient boosting machines, so if all the residuals are zero, it means that the previous prediction was actually accurate because the difference between the prediction and the actual value is zero. So if the previous prediction is accurate, so we don't want any weight for this node. Okay, so we will zero, the Wj will be zero. So this is in accordance with the boosting framework, where we want to avoid, where we want to pay more attention to examples that were misclassified or had errors. Okay, so if we don't have an error, so we will discard it. And one more thing is that the lambda variable here, it serves as an regularization term, and we see that the larger lambda is, so the smaller the weight will be. And it is in accordance with how we define lambda as the coefficient of the weight in the regularization term.
The bigger W is?
Sorry?
The bigger W. So the smaller lambda causes to W.
Oh, yeah, you're right. I said it the other way.
Okay.
Yeah, you're right. Yeah. So one of the first tasks I had when I came to NICE was to explain, or the team, my data science team, how come, or do we even need to apply regularization when we use XGBoost, right? I mean, most of the machine learning algorithms we know, we have, before applying the algorithm, we have to apply normalization, right? So I dug into the web and I found this explanation of Tianqi Chen, which is the key author of XGBoost, and he said that you do not have to normalize the features prior to using XGBoost. And this got our whole team very surprised, because we were used to having to normalize the features prior to. But if the author of the algorithm said that you don't have to do it, well, maybe he's right? But so it drove me really curious, and I tried to explain why is this the case. So I came up with this kind of intuition, and you're welcome to tell me if I'm wrong. It's just an intuition. So let's say we take a function which is, in this example, x to the power of 10, and we calculate the ratio between its first and second derivative. We end up with this expression. Now, let's say we scale the original x by some factor, let's say 10, and we define a new function g. So if we again calculate the ratio between the first and second derivative, we end up with the same result. Now, what does it mean? It means that if we take a look at the term from the weights, we have here exactly this ratio between the first order derivative and the second order derivative, up to some value lambda. So this means that, as we saw here, the ratio between the first and second derivatives tend to be in the same order. In this example, they were the same, but they sort of cancel out. Okay? And this is why you really don't have to apply a normalization to your feature, because you will end up having the gradient and the Hessian cancel out each other. On the other end, in any other gradient descent machine, the gradients tend to explode, and they don't have the Hessians in the denominator to cancel them out. So this is why we normally have to normalize
Since the Hessian is always second derivative.
Yeah.
And
okay. So yeah, here we have we plug in the optimal value for W star in the objective function. We get this really cool term, and here, and this allows us actually to say how good is our tree. Okay, let's say we build a tree, and this will give us some kind of score for the tree. So we will, let's say for this tree, if we want to evaluate it, then we plug in those values that we just calculate, and the smaller the score is, meaning the better the structure is. I'm just running on it now because we've run out of time, but let's say a couple of more minutes with your permission. So let's say we want to plug in a different loss function. Instead of squared loss function, let's say we want a log loss function in the case of the classification problem. So this is the term for the log loss function. We can calculate the gradient of the loss function with respect to previous predictions. You have here the calculation that I did. You end up with this really nice and simple term, the same for the Hessian. And then if we want to kind of apply this kind of loss function in our algorithm, then all we have to do is define the loss function in code over here, and you can see that all we have to do is plug in the gradients we've just calculated. It's spreads minus labels, meaning pi minus yi, as we saw in the previous step, and the Hessian. So next question. To apply your custom loss function in XGBoost, you'll input the first and second derivatives with respect to Great. So let's continue. We also may want to use some kind of custom error function, which is more suitable for classification problems. And then we just plug in the function we define into the XGBoost algorithm. Okay, so one last thing I want to emphasize, growing trees, the intuition. In the process of deciding whether we want to take a split, yes or no, what we can do, if we define the node set of a given node and its left and right splits, then we can calculate the loss function without the split, and then calculate the loss function with the split. And then we can say, okay, let's calculate what's the difference. What do we earn from making the split? Okay, so we have this really cool algebraic formula that things cancel out. It's really beautiful. But what's really important to understand is that while in decision trees, like we decide on splits based on some kind of metrics, such as Gini or a
information gain.
We're over here. We are deciding on splits based on the directly deriving the loss function, which is really unique, right? We don't need any kind of external proxy for how to do the split, but we directly optimize the loss function. So this is the split criterion. And another question would be, what happens if all the GIs are zeroed in this expression? The first option is we make a random split. Second is we avoid splitting. We choose IL and IR that maximize the loss difference. Or we stop building the tree and add it to the ensemble every. Okay, so you didn't agree with my answer, so let me just give my explanation. Hope I will convince anyone. So if all the GIs are zeros, it means that actually, as we said earlier, the residual, for example, with the residual, all the examples in this node were classified correctly. So in this case, we don't need to further split. Okay. So this item split, we'll skip that. Handling this in data, XGBoost assigns a default direction in each split according to where the gain is optimized. Skip the precise explanation. This is a summary of the XGBoost theoretical steps. You can see that I tried several other regularizations and ended up with different split formula. You can try your own regularization techniques. Here you have a link to the Shiny app I prepared for you. I will also send it to you via email. And just to recap on the comparison between XGBoost and deep neural networks. Hope it's more it's clearer now. And just two last questions before we go on. So who is the lead author of XGBoost? So it's either Andrew Ng, Geoffrey Hinton, Tianqi Chen, or Isaac Newton. Great. And the next question is, this is again a recap, and the last question is, for which type of problems will you try to use XGBoost? structured, relatively small data sets with missing values, unstructured, huge data sets without missing values, structured, huge data sets without missing values, or I'll always prefer deep learning over XGBoost if I didn't convince you. Great. So in case you have any questions, then this is the time. Okay, so the winner of the competition is Vikram. Second place is AJ, who that is, and the third place is Kieran. Well done.
Well done, guys.
And thank you for participating.
Thank you very much, Amir. For that fascinating
Thank you, Amir. Thank you, Danny.
Thank you very much.
Talk to you then. Bye-bye.
Bye-bye.